Hello everyone, I'm Norman Wahlberger. We're going to talk about time contraction and length dilation in special relativity. But it's special relativity with a bit of a twist. This is a simplified Euclidean version of special relativity. So instead of looking at Lorentzian or sometimes Einstein/Minkowski geometry, we're looking at a much more familiar, everyday, perhaps understandable version, which still retains a lot of the features of the subject, enough to understand this basic idea that the Lorentz transformations, which drive a lot of the remarkable conclusions or consequences of special relativity, are still happening in this situation here and can be understood in a very simple way as simply change of variables. So what we're doing is we're just going back essentially to first year linear algebra at a university level and a very simple diagram. Now I appreciate that many of you sociology types might not be that versed in mathematics, so I'm going to really try to lay this out very simply, and I'm going to ask the patience of those who are a little bit more sophisticated mathematically or physically. But I think you will be rewarded because you're going to see some familiar things in an unfamiliar fashion, perhaps. So the entire lecture today is my attempt to explain this diagram. And what we want to see initially is this rectangular coordinate system, which is very familiar from high school, the Cartesian coordinate system. However, the x-axis is as it usually is, but this one here, instead of being called the y-axis, it's called the t-axis. And this is actually x sub a, t sub a, because we're thinking of this as representing the point of view of observer number A, and there's soon going to be a second observer B. Okay, so what do we see in this picture? So it's just really Euclidean geometry, and Euclidean geometry is all about, in some sense, the consequences of looking at a circle. This is the unit circle with the equation x squared plus t squared equals 1. So this whole space here, we're going to think of this as time space. And crucially, we want to regard this vertical axis as the first axis and the horizontal axis as the second axis. Okay, that's why I'm calling it time space, because we're going to interpret this direction as representing time and this direction as representing space. So what's the sort of physical meaning of this? Well, this is very much like the usual story in special relativity. We imagine that we're describing one-dimensional motion, okay, say in this direction here, and we have coordinates here, so we can say where we are. So this is position 3. And this coordinate here represents the time of events. So for example, this point here represents an event which is happening at this position, marked -1, but at time 3. So its coordinates are 3, -1 in this A frame. Okay, good. And now we're going to introduce a second frame. So then this introduces the idea of a change of basis matrix in linear algebra. So the question is, how do we go from understanding positions in this A frame to this new frame, the B frame? So we see that what we've done is we've taken these coordinate axes and just sort of rotated them sufficiently. And actually we've specified exactly where we've rotated to, because that point there is the point 4/5, 3/5 on the unit circle. So it's 4/5 in that direction, 3/5 in that direction, and that is indeed a point on the unit circle, because this thing squared plus this thing squared equals 1, because 4 squared plus 3 squared is 5 squared. That's the standard Pythagorean triple that goes back thousands of years, 5,000, 6,000 years at least. Okay, if we rotate like this, and it's not too hard to see that this other point here will have coordinates -3/5, 4/5. So that's its coordinate representation in the A frame. But now we want to think about coordinatizing everything in this green B frame. So here are the coordinates 1, 2, 3. So same lengths as these ones. And here 1, 2, 3 in this direction, etc. Okay. So now in this green coordinate system, this point P, its coordinates are actually 1, 0, because it's 1 in the time direction and 0 in this direction here. And what about this one here? What would it be? Well, the time axis, the way you get that is you look at this x-axis here and you translate up here, okay? And you go, okay, parallel to this one here. And where that meets there will be the t-coordinate of this point here. And to find the x-coordinate, we'd have to go in a direction from here parallel to this line. So we move this parallel over here and we get some coordinate over here, okay? Maybe a little bit more than or a little bit less than -2. So this point here, which had coordinates 3, -1, is going to have coordinates which are roughly 2, -2, but not exactly. So what are they exactly? Well, in linear algebra, we learn very important sort of transformation, how to go from one coordinate system to another. And the point is that a matrix, like this, a 2x2 matrix, is involved, either this one or this one, depending whether you're going from B coordinates to A coordinates or from A coordinates to B coordinates. And there's a little bit of matrix multiplication in here, so just to practice that, let's have a look at taking this point here, which in the A system is the point 3, -1. So we know what TA and XA are. They are 3, -1. And let's multiply by this matrix and check that we're going to get reasonable values for T sub B and X sub B as this thing claims. Okay, so 3 -1, so that'll be 12 minus 3, so it'd be 9/5. So that's just a little bit less than 2, okay? That would be there. And the second coordinate would be 3 times -3/5 plus -1 times 4/5. So that's -9/5 -4/5. So that's -13/5. And -13/5 is between -2 and -3. So if we went like that, yeah, it's sort of pretty close. Okay, so this point here has coordinates 3, -1 in the A system, has coordinates, what did we say? 9/5 and -13/5 in the B system. And this matrix here allows us to go from A coordinates to B coordinates completely consistently. This point here, okay, its coordinates are 4/5, 3/5. If we plug in 4/5, 3/5 here, you're going to get 1, and over here, you're going to get 0. So the system does work. We are, in fact, going to get 1, 0 if we plug in 4/5, 3/5 here. And you can check the same thing as here. The coordinates of this thing in the B frame are 0 and 1. And this equation up here is just the inverse matrix. So if you invert this matrix in linear algebra, then you get this one. And this allows you to go from B coordinates to A coordinates. Okay, so that's all very simple. Just a sort of a quick review of some elementary change of basis kind of stuff in elementary linear algebra in a first-year course. So what does this have to do with special relativity? Well, let's now interpret these coordinates to be times and positions. So what we're thinking about is that these vertical marks here represent the ticking of a clock, of A's clock. Tick, tick, tick. So when A wants to record the time of some event, let's say, how about, there's another event, okay? So what's the time of that event? Well, 0 tick, 1 tick, 2 tick. This will be somewhere between 1 tick and 2 ticks. It'll be 1, maybe 1.3. That will be the time coordinate for this thing here. This represents the spatial coordinate, which is the obvious thing, a little bit more than 3. And similarly, we have the same interpretation for B. This thing here would be pretty well a little bit less than 3 for the time with respect to B, and a little bit less than 2, the x-coordinate for the B frame. So now what we want to do is we want to compare the basic units of one of the systems from the point of view of the other system. So this A clock is ticking tick, 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 etc. While B's clock is ticking tick, 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 tick. So suppose that A listens to B's clock and listens to the ticks. What's he going to find? Well, the first tick is here. This next tick, represented by this point here, will in A's frame have time coordinate 4/5. And then the next one is here, will have time coordinate, well, it'll be 2 times that, it'll be 8/5. And then the third one will be over here. So A registers B's clock as ticking faster. Listening. So A's clock is going like this, and A is listening to B and hearing something like this. Faster. Okay? So that's actually the opposite of what happens in the special relativity story that's familiar. There, that situation is called time dilation, so it's reasonable to call this time contraction. Okay, but what about the other way around? Suppose that B is listening to A's clock. So here now we're looking in B's frame. Tick, 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 tick. And B is listening to A's clock, which this one, this one, this one. So when this one ticks, what time is that in the B clock? Oh, we just have to go parallel to this. It's right about there. Well, it turns out that's also 4/5. And then the second tick up here will correspond to that time in B's thing. We get exactly the same story from the B's point of view. So it's not as if A thinks B's clock is ticking faster and B thinks that A's clock is ticking slower. They both think that each other's clocks are ticking faster. That's time contraction. What about length dilation? Length dilation has to do with rulers. So now we're talking about the spatial direction here. So let's look at A. Right, A has marked off the spatial component with this kind of thing here. You implicitly see something like a ruler, right? Say from 0 to 1. That's the basic unit of displacement that A is using. Now, as time goes on, okay, as time goes on in these space-time or time-space diagrams, this observer here is represented by this vertical line. That means that the end of this ruler that he has at 1 here will also, because it's stationary with respect to him, will also be moving in a parallel fashion in his frame. So in other words, if we look at if he looks at the ruler at some later time, maybe at time 2, where is the ruler going to be? The ruler is going to be in the same position. All right, so this end of the ruler is making a path in the time space. It's called a world line in physics, usually, which looks like this. Okay, just the vertical line parallel to this one. So these are the positions of the end of the ruler through time. So let's look at this ruler from the point of view of B. Here is B, okay? So how is B going to measure this ruler? Well, at this end, he knows that its end is here, but in order to make a length reading, he wants to look at this, like this ruler here, right? This ruler might be doing something as far as he's concerned because he's actually moving, right? B is actually sort of moving this direction. So the ruler is moving. But what he wants to do is he wants to measure the ruler in a way so that he's measuring the endpoints at the same time. Right? It doesn't make sense if the ruler is moving like this. It doesn't make sense for him to measure this one, this position now, and then wait a little while and measure this position now at some later time, because then he's going to get a distorted view. He wants to make the position measurements of the ends at the same time. What that amounts to is that he has to look on the world line of this ruler at the place where that end of the ruler is going to be at the same time as the beginning of the ruler. So the beginning of the ruler is right there. That's at that time. And so the corresponding other endpoint is going to be sort of simultaneous with the left endpoint exactly at that event there. And so that is then the key for him to measure the length of this ruler. He's going to look, okay, well, that's at 0. Where is that at? Oh, that's at something a little bit bigger than 1, actually at 5/4. But anyway, it's something bigger than 1. So B observes that A's ruler does not have length 1. It has a length bigger than 1. This is length dilation. And it works the other way around too. So for example, if we look at B's ruler, that will be this segment here. Okay, this endpoint is known to A, but this endpoint here is moving, and it's moving in a way that's parallel to this one here. It's actually a little nice little exercise to actually compute exactly where it goes. So it goes something like that, and it's going to meet the A spatial axis at that point there, and you see again exactly the same as before. A will read that the length of this ruler of B is actually more than 1. So this is length dilation. And that's all it is. Time contraction and length dilation are purely, there's nothing magical, there's nothing mysterious. It's just a consequence of having two different reference frames in the plane and comparing how one measurement system looks like in the other person's measurement system. Now you would say, well, what about the usual special relativity? It's really very much the same story. In fact, the whole thing can be pretty well obtained by this one just by sort of a judicious small change in the numbers involved, and this circle ends up being replaced with a hyperbola in a reasonably straightforward way. But conceptually, okay, if you've understood this story here, then it's relatively a piece of cake to understand the special relativity story, the usual one that's presented in all these diagrams. And I want to emphasize to you again that this shows again, I think more and more clearly, that the time dilation, length contraction that we usually talk about, these are observational effects. It's not as if anything is really happening, or, well, that's a philosophical question. Is something really happening? Well, I mean, we're talking about observations of the world. And those observations are very real. But we shouldn't think that there's some physical process of something actually shrinking physically or something, actually changing its internal workings. No, it's just that it's being looked at from the outside from a different point of view and something different is being seen. That's all. I'm Noah Wildberger. Thanks for listening.